Hello and welcome to today's webinar, Enabling the Python API for the AUTOSAR Adaptive Platform. I'm Brendan Morris, Senior Technical Marketing Engineer, and this is based on a white paper by my colleague Caroline Molnar, Enabling the Python API for the AUTOSAR Adaptive Platform. This is available from mentor.com/AUTOSAR to download. Today we're going to talk through a little bit of context of where this fits in the Siemens portfolio and capital. The industry context and thus the motivation for why we've developed this, and then we'll look at the implementation, including some examples. So first, a little bit about capital. We've built up a complete EE systems development solution under the name Capital, covering all aspects of electrical development for vehicles. Starting with requirement system models, architecture, working both down the electrical systems harness development path and, of more interest today, the software and network development environment at the top. Today's discussion focuses on package that's part of the Capital Embedded section. So let's discuss the changing industry, the disruptive trends that are feeding into our motivation to do this. As we all know, vehicle electrification is happening everywhere to everything from micro hybrids all the way up to full hybrids, plug-in hybrids and full electric vehicles. At the same time, we have increasing levels of driver assistance, automated driving being fed in, driving electrical complexity. On top of all of this, there are ever more government regulations around the world, new business models being brought in by competitive startups, and really aggressive commercial challenges, especially right at the moment. I mentioned autonomous drive. This is really adding a lot of complexity both to the development and the vehicles, but also to the platforms that are reused across multiple vehicle lines. In the case of autonomous, we're adding tens of new sensors, hundreds of thousands of lines of extra software code, a lot more expensive electrical hardware. We have constant challenges with extra safety and security consideration, extra validation goals we need to include. All of this drives new architectures and ever increasing amount of data around the vehicle. Looking a little bit more at that data aspect, only a few years ago, 2014, Deutsche Bank did some research and predicted that by today we would be looking at vehicles with maybe 30 million lines of code and 10,000 signals. This has turned out to be quite a big underestimate. We're seeing premium vehicles with level 2 and maybe some level 3 ADAS functions with 150 million lines of software code and 20,000 network signals, and this is only going up. So let's look a little bit at AUTOSAR. AUTOSAR is now the dominant standard for automotive software. It includes not just a standard for the basic software for the middleware, but also abstraction layers for the hardware and application software to support reuse and a full development process. The standard's been around for nearly 20 years, started in 2002 with its first major release in 2005, and is now used by all the major OEMs and many of the tier ones. More recently, the AUTOSAR Adaptive Platform has been introduced. This is targeted at service-oriented architectures. This had its first release in 2017 and is really designed to coexist and interoperate with AUTOSAR Classic as the traditional AUTOSAR is now known. To support this, the AUTOSAR standard is now split up into the Classic Platform, the Adaptive Platform, and a Foundation Platform which covers the services, the functions needed both Classic and Adaptive platforms. So if we look at how that's used, we're used to traditional multi-bus gateway architectures, usually multi-CAN gateway architectures that have been quite common for the last few years. And all of those ECUs are likely to be AUTOSAR ECUs. More recently, many OEMs are moving towards domain controller architectures with really functional domains. Each of these grey ECUs is likely to be AUTOSAR Classic again. We're likely to be using higher baud rate networks, and we're likely to have introduced automotive Ethernet as a backbone. And this opens the opportunity of not just traditional communications, but potentially service-oriented communications. So we start to think about the options that something like adaptive AUTOSAR gives us, rather than classic AUTOSAR where everything is pre-configured, standard and fixed. This then opens the door to the future that most OEMs are looking at with zonal architectures, where we really start to go much further into the service-oriented environment, where the computing is centralized in the vehicle, and the zonal outstations are more likely to be a product of the layout of the vehicle and where sensors and actuators and ECUs are needed, rather than a functional split. So let's look a little bit more at the motivation for developing this package. We see a real use case in rapid prototyping. There's an ever-increasing need to move rapidly, building proof of concepts, testing new ideas. It's particularly relevant in the areas of autonomy, ADAS, but there are many bits of functionality we're constantly wanting to add to new vehicles. And in these early stages, we need to quickly build proof of concepts. We want to build up bench tests, models, and even get functionality running on prototype test mules. And the timeline can be very demanding. We often have multiple technical solutions we want to evaluate and understand if we're on the right technical path before we commit to full production development. We also see that with this increase in autonomy and ADAS functionality on vehicles, there are more data scientists and researchers coming into automotive. Commonly, these are machine learning experts. And although they have strong C++ programming skills, the sort of native language used or languages used in machine learning tend to be high-level languages. Enabling the use of these high-level languages, such as Python, would reduce the need for C++ and AUTOSAR specialists, returning the focus back to the research work and building these proof of concepts. We should get shorter development cycles, improved work efficiency. When we analyze these high-level APIs widely used in machine learning frameworks, it's easy to see that the Python language is the dominant language. It's overwhelming. And although the intensive computations are still programmed in low-level code, Python can be used for defining, configuring the algorithms in high-level code. This allows the researchers to focus on the mathematical problems instead of dealing with the software and computation issues and debugging quirks of C++. To close this gap between these high-level APIs and the machine learning frameworks and their automotive applications, our engineering teams have created a set of Python packages for the AUTOSAR Adaptive Platform. These packages are intended to support simple, high-level access to the AUTOSAR APIs. So let's look at some of the implementation decisions we've made. There were two Python API options: build and completely replace the C++ runtime, or build a binding layer on top of the C++ runtime. And both have advantages, but we saw more benefits building a binding layer on top of the C++ runtime. This gives us a smaller code base, better CPU load balancing using the C++ multi-threading, and reuse of standard C++ components. There's years of automotive knowledge encapsulated in AUTOSAR from across the industry. Implementing new persistency and logging code could be quite a simple activity in Python, but we would lose the redundancy and encryption built into the standard AUTOSAR adaptive persistency, and we would lose all of the capabilities of the standard dynamic log trace built into AUTOSAR. To also see the AUTOSAR COM binding provides the facility to perform service-oriented communications for Python applications. The COM binding provides the facility to perform service-oriented communication for Python applications, where the API is dynamically generated from configuration. A related Python API is generated. Primarily, this is applicable to the COM in this iteration of the solution, and generator is using the same artifacts as the C++ generator backends. This means there's no additional configuration needed for the Python bindings. In certain functional clusters, the Python APIs remain static, such as logging, persistency, execution management, following the behavior of the underlying C++ implementation. So another decision, the API syntax. Our approach mimics the C++ APIs as much as possible, as we'll see shortly. The aim of this was to minimize the transition when we decide we've got the right technical solution. When we move from proof of concept through to full production code, this should be as easy as possible. The initial set of binding packages are available for the communication manager, persistency, log and trace, and execution management. And you can see here an architectural overview of how that looks. The goal is to provide a Python API facility for a set of features that will be immediately usable for the algorithm developer, for the research engineer. The APIs were developed to support the 1903 AUTOSAR specification, but updates to that is something we'd be interested to discuss. Practical implementation. Let's look at some code examples. Communication. The language binding supports publishing of and subscribing to services for service-oriented communications. APIs are used to handle the events, methods, and fields, and are available on both the proxy and skeleton sides, including all the necessary core. AUTOSAR Adaptive COM APIs, both on proxy and skeleton side, are heavily configuration dependent. Therefore, the binding layers built on top of the generated C++ APIs are dynamically created as well. In this example, the imported package is generated Python module wrapping C++ interfaces. In order to initialize and use the features from the Python, the same steps must be performed as in the C++ counterpart. We can see if we look at the Python on the top and the C++ below, as we mentioned before, the syntax is very similar to make the conversion process from the proof of concept to the production code as easy as practical. Log and trace. Logging is fully supported. Logging data is reported as string for convenience. The steps of initializing the logging, creating context, are the same as in C++. Similarly, after the logger context is created, actual logging can be performed via the usual methods. Again, the syntax is as similar as practical. The Python at the top, the C++ below. We look at example of the init logging and even the sequence as similar as possible. Persistency. The supported features include both key value storage and file storage type of persistent storage. In this example, the key value storage persistent storage mechanism is used with an underlying database, which is a JSON file in our use case. A value is written and another is read from the database. Again, we can see the write and the read, and they're very similar in both the Python at the top and the C++ below. Execution management. The API set of the execution client class are fully supported. This allows Python applications to report back their operation status to the execution manager. And again, an even simpler example. And again, Python above, C++ below, and it's very similar indeed. Machine learning support. A detailed example would be too much for this webinar, so we've included just a few lines of code to demonstrate the simplicity of using a machine learning framework with the AUTOSAR Adaptive Python Binding API. In this example, the results of a random loss calculation of a PyTorch model are provided via service elements. This can be seen in the unhighlighted text 2/3 of the way down, which is much simpler to do in Python than it would be in C++. The yellow marked lines are related to the AUTOSAR Adaptive COM functionality for service initialization and event sending. The blue marked lines are for logging to the AUTOSAR Adaptive Log and Trace. So, what's left? While the covered functionality and a number of supported APIs may grow over time, there are a number of domains that are just not practical to introduce in interpreted languages. Therefore, out of scope are safety-critical operation and hard real-time behaviors. OS support and third-party. OS support and third-party code. The Python package provided by Mentor runs on desktop Linux out of the box. A Yocto project-based Linux can also be used with minor configuration. Upon request, other embedded solutions can also be supported. And so a quick summary. The complexity of the system and the performance-oriented C++ API can make it difficult to use in the early proof-of-concept development phases, research phases of projects. Using Python binding provides a synergy between the simplicity of the Python language and the versatility of the AUTOSAR Adaptive Platform. Python being the most widely used of the major machine learning frameworks languages, helps data scientists with academic backgrounds deliver results quickly for automotive prototypes. And the resemblance of the API names that allows the team to quickly familiarize themselves with the AUTOSAR concepts and the syntax of the final C++ product, thus speeding up that conversion process to production later. Recognizing the gap between the high-level APIs, the machine learning frameworks, and their automotive application, our engineers have created a set of Python binding packages for AUTOSAR Adaptive Platform. These packages provide simple, high-level interface between the Python programs and AUTOSAR Adaptive. To learn more about the white paper that this is based on, Mentor's involvement in AUTOSAR, please visit mentor.com/AUTOSAR. Thank you.